A special class of matrices is the Laplacian matrix. We often have a physical domain if we're modeling something or writing a simulation, and then we can use that domain to parallelize because we assign subdomains to processors. Sometimes they are contiguous, in most cases they are contiguous, and then communication is only across the boundaries of these subdomains. Sometimes the application is very regular. We have a multidimensional grid, a rectangular grid. It could be 2D with neighbors always to the north, east, south, and west, or it could be 3D. An example is the heat equation, where every grid point is influenced by the temperature of the 4 surrounding neighbors. So let's study the two-dimensional Laplacian for a k by k grid. And this Laplacian operation is basically adding all the values in the neighboring points and subtracting 4 times your own value. That will be the new value. And what's the reasoning behind this? If we take x in the point I plus 1j minus xij, that's the first derivative, or approximation to the first derivative of the temperature in that direction. And then if we subtract 2 such terms, then we get the second derivative. So the second derivative is basically taking the point to the left, point to the right, adding them up, and subtracting twice your own value. And if we do that in both directions, we get the Laplacian shown on the top. So that's the Laplacian operator. Now, we can translate this grid to a vector. For example, a 3 by 3 grid corresponds to a vector of length 9. And for every grid point ij, we define I plus 3 times j, or in general k times j, as the corresponding index of the vector component. And then we can view the x's as the input and the deltas as the output. And so, for example, for the input xij then becomes the component I plus j times k of the vector v. Now, the corresponding matrix is the matrix A that you see here with -4 on the diagonal and with 4 diagonals containing 1s. And then this corresponds exactly to performing the Laplacian operation. It's if we have u equals A times v. Now, looking at the formula for the Laplacian operation, you see that you actually only have to perform 5 flops, because 4 additions, or 3 additions and a subtraction, and then multiplying by 4. So that's why we say this is 5 flops if we carry this out. So sometimes we prefer the domain view, and sometimes the matrix view. Here we will take the domain view. In most cases, that gives a natural partitioning of the space, for example. But sometimes we learn something by also having a look at the matrix view. So for a 2-dimensional grid, which we will study first, we say that we have 5 flops for every interior grid point, not at the boundary. We have 3 flops that we have to perform for corner points. And in the middle, or at the boundary but not a corner, we have 4 flops that we have to perform. And here you see a grid, 8 by 8 grid. And to the left, you see that we have altogether 4 processors. And these 4 processors, they all get a strip. So we cut in 1 dimension. The total amount of communication that we then need is, if you take the processor, that's the 2 processors in the middle, they have to get something from the left neighbor, k values, if it's a k by k grid, but also from their right neighbor. So altogether, the processor that has most needs to get 2 times k times g. That's the communication cost. We can, sometimes if we don't like the load balance, and that can happen if you have an 8 by 8 grid and 3 processors, you can do boundary corrections. So you cut in the vertical direction, but you make a little indent and you jump to the left or to the right. And that way you can improve the load balance, and it doesn't influence the communication by much. But of course, why split only in one direction? If you split in both directions, then you get a lot less communication because your periphery is smaller. In this case, if you have a square, each side of the square has length k divided by square root p, and you have 4 such sides. So altogether, the communication cost reduces to 4k divided by square root p times g. Now we can have a look at the communication to computation ratio, and that's the numbers that we just saw. So the communication for the squares was 4k divided by square root p times g. And the computation, if we have 5 flops per grid point, and we have k squared grid points overall, but k squared divided by p per processor, then this gives us 5k squared divided by p as the cost of a computation. And then dividing these, we get a ratio of 4 times square root p divided by 5k times g. This is also called surface to volume ratio. And then we use the terminology of 3 dimensions, because the surface is the boundary across which you communicate. And the volume, that's all the grid points for which you have to compute something. So sometimes it's called surface to volume ratio. Now here I have a question for you. We take the 12 by 12 grid. We have 8 processors, and we split it in a quite natural block fashion. Every processor gets a subgrid of size 6 by 3. And now assume that we have a G of 10 and an L of 50. What is the BSP cost of the Laplacian operation for this distribution? And the Laplacian operation is basically a sparse matrix vector multiplication. But we only have 2 super steps here, because you obtain data from your neighbors, what you need, and then you perform your local computations. So what is the cost? Most likely you paused for a moment and took pen and paper, and I hope you got the right answer. So for computation, the processors that have to do the most work are the 4 processors in the middle, because they have the 18 points, 15 of which are interior points, and only 3 are boundary points. So those 15, they give 75 flops. The boundary points give 12 flops, so they have to perform 87 flops. The corner processors perform fewer flops because of the boundaries. Then the communication that we have. So every processor has 6 neighbors to the left, 6 to the right, and 3 to the top. Well, not really. Every processor, the same 4 processors that we just saw in the middle, they have this number of neighbors. So they altogether 15 neighboring grid points. So the information they need to get is 15 values. And now, so we know that the H for receiving is 15. But what is it for sending? Well, you see, if we take one such block then 6 points to the left, they have to send their value to the processor that is to the left. 6 on the right to the ones on the right. And the values in the corners on the top, they have to be sent not only to the left or right, but also to the top processor. So those values have to be sent to 2 different processors. And altogether, this also gives 15 sendings of a data word. So h equals 15, and the communication cost is 15 times g. And here, performing the Laplacian operation, we only need 2 supersteps, so the cost is 2L. Then if we substitute g equals 10 and L equals 50, we get 87 plus 150 plus 100 is 337. Keep this number in mind to compare to what we do later. 337. So blocks are nice, but we can do better than that. We have diamonds here. And a digital diamond is defined by, you have a center, C, and a radius, R, and all the grid points that have a Manhattan distance of at most R to the center point. So they are, in this picture, the radius is 3, and you see that every black circle is at most 3 edges or blocks, if you want, if we talk Manhattan language, away from the center. So if we use a diamond as our basic cell assigned to a processor, then, well, how many points are in the diamond? If you count carefully, it's 2r squared plus 2r plus 1. And then if we think of having p processors and each gets its fair share, then we have that this number of grid points equals k squared divided by p. That's what we hope to achieve. So in approximation, 2r squared equals k squared divided by p, and that means that r is k divided by square root of 2p in approximation. That's about computation. Now about communication. Let's just look at what we receive. That's easy because we just count the number of neighbors. And the number of neighbors of a diamond with radius r is 4r plus 4. So then we can compute the communication to computation ratio, which is 4r plus 4 divided by 5 flops times the number of grid points in the diamond. And then if we only look at the main terms, this is 2 divided by 5r times g, and we can substitute our approximation for r. And then we get 2 square root 2p divided by 5k. And this 2 square root 2p is a factor of square root 2 less than we had before. So diamonds are better than blocks, if we can use them. So now we want to tile the whole space. And here you see a lot of diamonds. Someone very dear to me shows them. And indeed, we can tile the whole sky with diamonds if we do it this way. We have a center, and then we take a direction A, which is r to the right, r plus 1 to the top, and B, which is minus r minus 1, so r plus 1 to the left, and r to the top. And then we take multiples of these vectors A and B, lambda times A plus mu times B, and these become the centers of all the tiles. And lo and behold, they fit exactly. And then if we have a square grid, we can superimpose that, you see it, and then we just take the tiles and we cut off anything that we don't need, and we get a nice distribution. But it's not very practical because it doesn't completely fit. And you have to be lucky with the size. And now, a little improvement is if we take one such tile and we remove the boundary, the northeastern boundary and the southeastern boundary. So the eastern boundaries, we remove them. And why do we do that? Because then we can take the same tile, shift it to the northeast, and then we have the start of the next tile at our boundary. And that way, we get this picture that we saw from the Alhambra exactly. The number of points inside the diamond decreases, in this case from 25 to 18. But we can fit them together based on actually squares. And that's the picture that you see here. So this is a 12 by 12 grid. What we did is we used periodic boundary conditions so that if we cut a part, then we connect it to the other parts. For example, the 4 corners all go to the red processor. And if you count what the BSP cost here is, it is 330, which is less than the 337 that you computed, hopefully, for the previous block distribution. So this is already an improvement. Of course, it doesn't feel very right to have 4 corners that have nothing to do with each other but assigned to the same processor. So you might ask yourself, can we improve this? By the way, how did we get to this number of 330? We count for every processor, we count how many grid points it has, and also if they are interior points or boundary points. And the maximum that we get for a processor is 90. And of course, it's the black processor in the middle that only has interior points that has the maximum. And then we can also, for every part, we can count the number of neighbors. That tells you how many data you have to receive. You count how many you have to send to data. Sometimes you have to send to 1, 2, or 3 neighboring points, the value of your own grid point. Here we see that the maximum is 14. And that gives a cost formula of 90 plus 14g plus 2l. That's how we got there. But then what we can also do is we translate the domain, the problem, to this sparse matrix, feed it into our matrix partitioner Mondriaan, where we tell it that every grid point connects to a row of the matrix. So we ask Mondriaan to keep rows together. So it's a 1D row distribution that Mondriaan creates. So it's not a default, but we can ask to do that. And then when we get the result, we translate it back to the grid. And this is what you get. It's interesting what you see here. First of all, the total cost is still reduced by a little bit, 329. You see 7 processors all have part of the boundary. Near the boundary, you have to perform less communication because you don't need to communicate, for example, from the left boundary. And all parts are now contiguous, which is a good thing. You don't have these disconnected parts. And you have one small part in the middle, the black part. Well, the middle grid points have to be assigned to a processor. But if this processor would also touch the boundary, you would probably have lots of communication. So this part is kept small, and it does have a lower communication volume. You can do this also for a 32 by 32 grid. This is what Mondriaan finds here. You see, always we get these skewed boundaries, not straight blocks. So that's what Mondriaan creates here. We can also do this in 3 dimensions. So in 3 dimensions, if we have a block distribution, we have cubic blocks. And the total number of points we call n. That's k cubed divided by p if the blocks are all of equal size. And then you can ask yourself, how many of those points are at the boundary? Now, a cube has 6 faces. The sides of the cube are, in this case, k divided by cube root of p, because altogether we have p processors. So we get a simple formula calculation, 6 times n to the power 2/3 as the total number of grid points, or the size of the boundary, which is a lot. For example, if you think about it, if the processor has a 10 by 10 by 10 block, then 8 by 8 by 8 are interior. That's 512 points. But 488 points, almost half, are at the boundary. So the conclusion is, in 3 dimensions, communication is much more important than in 2 dimensions. So we need to do something to reduce the communication. And we can get some improvement by using the diamond shape, also in 3D. So here I have a truncated octahedron. You can see through it. It has hexagons, 8 hexagons. It has 6 small squares. And these hexagons, they all go in a 1, 1, 1 direction, which is skewed. And that's nice because we saw that already in 2 dimensions. And now we can tile the space with these truncated octahedra. We can put one here, one here, one here. The hexagons connect them. And this is a nice object. It has the grid points inside. They go to a processor. You still have to decide what you do with the grid points that are exactly at the boundary. Now, this is WYSIWYG. You see, this one has 2 colors, yellow and red. And what you see is what you get. If you can see them, you get them. For example, this one, the yellow hexagon, is assigned to the processor. But the one in the back, the red one, is not assigned to the processor because it becomes part of the next processor. And the same holds for the edges that we have and the vertices. We have to share them between a number of processors. And you win some, you lose some. So this will work. And it actually gains you a factor of 1.68 in communication if you have the ideal case, and that is the number of processors is 2 times a cube. For example, you could have 16 processors. If it's a power of 2, then cube being 2, then this is an ideal case. There you would get this. OK, to summarize, you can use knowledge of the physical domain to reduce communication cost. And you need to cut all dimensions. For example, you get in cubic blocks in 3D, but you can do even better than that by having diamond shapes. The best performance in 2D you get if P is 2 times a square. In 3D, if P is 2 times a cube. Both cases, you have a digital diamond. In the 3D case, it's called a truncated octahedron. Now you can, in the final question, start solving the puzzle. We have this, again, 12 by 12 grid. You have 8 processors. We fix the values of the parameters G to 10, L to 50. Try to improve the solution found by Mondriaan. You can maybe draw some pictures and improve this, and it can be improved. So you could even go a bit further. You could write a computer program that tries to find an optimal solution. Some of my students have done that.